one, go.
Brilliant. So guys, we may as well do a little recap of last week, just the end point of last week where we reached, because you weren't here last week, and I actually think this part of the chapter with regarding the soft margin and optimization problem feeds in really well to the kernel trick and the support vector machine section in the chapter. So it doesn't hurt doing like a this time last week episode recap. So last week we actually ended on the note of when we discussed the tuning parameter C when it comes to our support vector classifier. So I'll just scroll up a little bit just to give extra context. And we were discussing last week how the support vector classifier basically affords us some flexibility. And as we know throughout the weeks, this is the classic bias-variance trade-off. So the question remains as to whether we can misclassify a few training observations as a means to achieve greater robustness to our individual observations, and do we accept more violations for a more stable generalizable classifier? So we can use a little bit of a discussion point here if you guys have read the first half of the chapter just to get ourselves settled, and we'll discuss a little bit about the tuning parameter C because that is very relevant in the number of support vectors we have in our margins, etc. And then we can go into the support vector machines and nonlinear decision boundaries. So last week we were asking ourselves like the classic trade-off question, in what use cases may it be better to accept more violations in exchange for classifier stability? And when might it not be helpful? So this is, I guess, not even just a model question, but also data question. When do you want to maximize your margin? And when do you want to have a narrower margin? And if we scroll down here, we can see that the tuning parameter, obviously with its narrow margins, you have lower bias and higher variance, so you potentially overfit. And with a smaller c, you will calculate wider margins. So you have higher bias and lower variance, obviously in the model, which is a classic paradigm. And with this comes the implication of, okay, are you going to have fewer or more support vectors? So if you guys have read the chapter, what did you guys think about that? Did you think, are there specific use cases where we want to maximize M, where we want to a wider margin, and when you want narrow margin or fewer support vectors? I know that's a very general question, but I don't know if you guys have.
Yeah, interesting. No, I did read the chapter. I didn't take very good notes though, so normally I could rely quite heavily on my notes.
Not, and there's no like right answer to it at all. I guess when I was reading it, I thought, oh, that would be interesting, like thinking about use cases, like when we want to fine-tune parameter C.
I suppose though that whether you are willing to like give back some flexibility, right, to like increase bias, but you're trying to reduce some variance. I think it feels like that's generally quite a good idea, just as a general principle. And I remember thinking as I was reading it, so let me piece this together. Like when it talks a lot about the feature space, right? And when you'd have reason to suspect, I think, that you're like, let's say you're missing features, like your classes aren't going to be so easy to separate, and maybe you don't have a lot of data. You might want to like you might want to like encourage a wider margin, because you might expect there to be more like noise with the low sample, but also like information that you're not capturing. So you don't want to like fit too perfectly to the information that you've got, because you know that you're probably missing some. I know that's kind of what comes to mind, but what did you have in mind?
So it was, I thought along those lines as well, and I thought it's almost better to afford that flexibility, as we'll see in a bit, than be too strict, I felt, in how you tune your C, because the observations that do lie on the margin or violate the margin, like in terms of where they're placed, they affect where you're separating the classes, like where your hyperplane goes. And that obviously has an impact on the model. So it's very sensitive in that sense. If you have, I think I don't know if I put it up here or down here, but there is a visualization I can send you guys after where you have your classes, which are, in fairness, very separable. And then you just add one or two observations, and immediately it's a different output just by adding one or two observations to the model essentially. And so I figured that when you have that sensitivity, I think maybe having that flexibility will afford you a better, like a more, I don't know, a more forgiving model in terms of what information you retain.
So sorry, so we're saying here in terms of flexibility, like have a allow for margin, or
Yeah,
to be strict on margin.
I think allow for margin. I think because when you have support vectors that do affect your support vector classifier, I'm wondering how wise it would be to be really to have that narrowness, or I guess or I should rephrase that, sorry, to have a low tolerance for violations. I don't know how much that would be useful, or not necessarily useful, but it would be quite stringent, overly strict, and you might not get all the observations that you want in your model to be classified.
And that's if you have the lower tolerance for the violations or the higher tolerance for the violations.
Higher tolerance, because sorry. Because you
Yeah,
have,
because
sorry.
sorry, Shrin.
Oh, sorry.
Sharon.
I was just going to ask. So in terms of the question earlier, in terms of like, do we think of specific use cases? So speaking of the higher tolerance for violations and the wider margin. So like in terms of use cases, like, are we talking about where, if you misclassify it, it might have a much more stringent possibly effect versus like a large C. So you have lower tolerance. So I don't know what's like a suitable use case for it, but I mean, raw comes to mind, but we're talking about having higher tolerance overall.
Yeah.
I don't know, is it,
Exactly, that use case of like fraud, as you say, like detecting that, because you want to be able to, that's much more important to withstand, like have fewer violations in that sense. Like that's more, you don't want, so my brain gets so confused with the large C and small c, because it's like it's inverse. Like my brain feels really tempted to say, oh yeah, large C, wider margin, but it's not. It's, I guess you almost want to, do you want to overfit in fraud? Because you don't want to wrongfully classify for non-fraud as fraud, no?
I think so. I would try to say, in my mind, separate overfitting versus balancing false negatives and false positives, and like the ROC AUC curves that it shows later.
Yeah.
That will be primarily a choice of like where your classification cutoff point is. And that will be related to distance from the like margin and where like the actual boundaries are being drawn. Because one of the ideas in the support vector machine is like further away from the boundary, you're like more certain it's in the class that you've put it in, and closer to the boundary, you're less certain.
Yeah.
But I would probably say in fraud, you might want to go the other way and try to not overfit so much, because you might think that or you might have this, and this is not like a modeling decision, this is just like an intuition,
Mm.
but you might have this idea that fraudsters will change their tactics.
Oh, yeah, yeah.
So if you like overfit past data too much, and those patterns, stop being being followed, then you might end up with a worse class rather than if you didn't overfit so much. But that would be a guess. I think like you'd have to test it like with data and see what happens.
Yeah, of course. No, that's an interesting intuition actually. It would be interesting to see that in an actual model, in a real-time scenario. So just again, some additional context with the optimization problems and soft margins. As we've like touched upon before, the parameter C's role basically obviously changes the margin size and it changes the number of support vectors. And so if we have noisy data, it's, as Jack mentioned, it's worth considering whether you want to larger or smaller C and Y. And with that, we start to come onto the question of, okay, well, real life data is not always separable. It's not always neat and tidy. It's not always linear. How can we address the optimization problem, i.e. choose which separating hyperplane in a certain data set when we don't have this stringent clean data. And this is where the support vector machines come in, where we apply the above from like the work we did in last week's chapter and just build on it. And we build on it by emphasizing, as Jack mentioned before, enlarging the feature space we have using kernels, the kernel trick, as the book affectionately dubs it. And we extend our support classifier to become a support vector machine. This is what happens when we enlarge the feature space. And I tried to explain it in, I guess, both layman's and not totally off the mark terms. But when I read the book, the way I kind of saw it was sometimes you have data that, as I've put it, looks like a donut, and you can't separate the inner and outer rings with a straight line. You can't say, hey, this is where we can classify cat versus dog definitively. So we use the kernel trick. Again, this is just me doing quite a generalized take on it. The kernel trick gives us the ability to see the data in different dimensions and where it becomes separable. So if you have that messy data, it enables you to the kernel trick allows you to be able to see a clearer picture as opposed to using our support vector classifier or the linear decision boundary. So to find out how our support vector machine solution, there's a few steps and some ways we can look at looking at our inner products, which is defined here as xi, xj between observations. And essentially, a given inner product of two observations can be defined in this mathematical notation here. And it's essentially calculates like a coefficient. It literally measures how similar two data points are. So that's useful if something is, say, far from zero or close to zero, and it gives you a better idea of, how closely together those data points are for the sake of classification. So again, bring it back to parameter C. The support vectors matter for making predictions. These are the ones that directly impact our support vector classifier. So this will ultimately come down to when we're fine-tuning and adjusting our parameter, which we'll see in the labs work. I think it's quite visible to see it. It's easier to see visually. This will massively influence the number of support vectors, and in turn, the inner product of our observations. So let's have a look at it in practice. Apologies for the typo. Our support vector classifier in this use case is just going to be linear, just so we get an idea of it. So in case you guys want to know, I've just used the code from the labs work. So we're going to fit the classifier, and I've set the C parameter to 10 in this use case. And I've set the kernel argument to linear. So we know it's a linear kernel argument. And as we can see here, this is the hyperplane. And we can see our margins as well. And I believe I've, so it's very linear, as you guys can see. And the support markers or support vectors are notated with the plus signs. And the remaining observations are plotted as just simple circles. So very linear, seems pretty, not to say simple, but it seems pretty clean in terms of how we can put them in set regions and classify them in our given observations. Now, let's just see what happens when we use a smaller value of the C parameter. Now, I did try to render this earlier when I tweaked the parameter, and this didn't change. So I actually have saved the visual. I can pop in the group just in case it doesn't render. Essentially, hopefully we'll see if it changes, but if not, I don't think it does. This is the code. I've changed it to 0.1. Now, it hasn't rendered the way I wanted it to do, but essentially it looks like all of these are smushed together and much more clustered. And again, I can provide the actual visualization because this unfortunately looks the same as before, which is very frustrating. But there is, I can attest, a giant change, a significant change in how the observations look, as well as the support vectors themselves. So I'll actually pop that in the repo or in the chat, whichever's easiest. So in an ideal world, when it renders, because we've shrunk the C parameter, we actually have we've gained a large number of support vectors because the margin becomes wider. And as well as that, you'll see in the visualization, the data space is punctuated by a lot more like clustering and closeness. So there is a significant change, say significant loosely, there is a change in the ways in which our classifying boundaries have set the observations and the support vectors. So we've looked at some linear ways of, or some linear kernels, but there are obviously nonlinear decision boundaries. These are essentially just, again, emphasizing the feature space and interactions between features. Here we have the mathematical notation for the polynomial kernel, and this just considers interactions between the features, like I said. And when D is greater than 1, the support vector classifier basically leads to a much more flexible decision boundary. So obviously, as dimensionality gets higher and higher, we are able to fit a support vector in a higher dimensional space when we're applying our polynomial kernel. And similarly, more consequentially or subsequently, we have our radial basis function kernel, or the RBF, where gamma is always the positive constant as it's in this parameter. And again, I've tried to find a way of summarizing or generalizing how the book describes it in a way that's interpretable. The way I saw it is that this is kind of like a locality kernel in that it describes the ways in which 2 points are similar if they're close together in space. So points that are really far apart are assigned almost zero similarity. Very similar to some of the clustering work we're familiar with as well. I have some discussion points, but please feel free to just chime in with whatever. But a couple of things that the book does talk about, but we can talk about them here as well. What is the purpose of the gamma parameter here? And also, what do you think is an advantage of using a kernel rather than just simply enlarging the feature space or using functions of the original features?
Can't remember exactly what the gamma parameter was, so I'll leave that one for you, Sophie. But the idea with kernels, right, is that like you might not be able to navigate an expanded feature space in any like reasonable period of time or with reasonable computation. And like I think it makes the case of like so if you're using like polar coordinates, or you've like you're using essentially the radius instead of like straight lines, so you can get it's like how you can get points back together by using like a quadratic transformation or something. But it makes the point that in that space, it's like there is an infinite number of calculations you could consider.
Right.
So it's like computational tractability is gonna be favored in using kernels. You reduce it was like you reduce it to like, was it choose as in like in probability theory, like when you choose, say, rather than like as in
Yeah.
combinations. And it's
Yeah.
like, say if you have 20 observations, you'd have 20 minus 1 times 2 calculations that you could make, and it uses that from memory in the book. So you don't scale so much with the size of the calculations you're going to make, basically. But what was the gamma parameter? I think I kind of skimmed over this a little bit.
Yeah, so again, I'm probably butchering this. I apologize, book, but from what I gathered, it's sort of a way of controlling the, like, I guess say the influence of individual training points or training examples on a decision boundary. And I kind of got the impression it's almost like it's not necessarily used in conjunction with the C parameter, but I guess gamma in a sense, in a similar vein, is controlling how, I guess, tight and loose is a really bad way of putting it, but I guess a smaller gamma means that the function might have large variance, and a higher gamma means that a Gaussian function has smaller variance. But I'm not entirely sure 100% how that might impact like the points in space or in I guess in, or how it impacts the decision boundary. I guess I guess if you've got a higher gamma and then let's say for argument's sake, then that function has a smaller variance, then only data points close to the decision boundary will impact the shape. So I guess that's more likely linked to overfitting because you have a very specific decision boundary shape, maybe. But I could be completely wrong, but that's kind of how I interpreted it in the book. But I'm not entirely sure.
I wasn't so with the gamma parameter, it's like as the exponent, what does it say? So as like the higher the value of the gamma parameter, the more flexible your model.
Right, yeah.
So like you get negative exponents, right? So like 10 to the negative 1 can really fit the training data almost like identically. It can maybe not memorize, but get quite close, like memorizing the training data. And as that value gets slightly smaller, like the exponent goes up to like 10 to the negative 3, then it gets less good at fitting the training data.
Right.
And less flexible. But you don't really care about training performance. You care more about testing performance.
Right. Yeah.
And then when you get to testing, you actually find that the 10 to the negative 1, like it's in not like a gamma parameter 0.1, will do better than the 0.001 or the 0.0001. And was this the bit where it likened it to some of the regression cases?
Yes. It was. There was the logistic regression like subsection, and I can't remember it now. But there was definitely discussing the similarities between logistic regression. And I think it talked about, did it compare it with lambda? I can't remember. I think I'm imagining that, but let me get it actually.
What I'm in the, was there also comparisons like the ridge regression stuff, or am I misremembering? I said, yeah, that does actually come maybe later, doesn't it, in the
Yeah.
relationship to the logistic. And okay, that's when we're on to lambda. That's when
Yes,
we're
that's
away
the
from
one.
gamma.
Yeah, that's the one. That's why I'm imagining it. Yes, it's yes, it mentions that the support vector machine is not unique in the use of kernels to enlarge the feature space to accommodate nonlinear boundaries. And basically, it's the book says we could just as well perform logistic regression on many of the other classification methods seen in this book using nonlinear kernels. So it's interesting.
Yeah, and I think there was the idea that maybe people thought it was very different to the methods, the statistical methods that had come before. But over time, they maybe realized that kind of the same idea, just wrapped up slightly differently.
Yeah, actually, it's interesting you say that because I think it's not from this week, but last week when we were going over somewhere like the mathematical definitions, even the mathematical definition of a hyperplane. If you see a hyperplane in 2D, it's a line, and you're essentially using the equation for a line. So it's built on very similar foundations that we've seen before. So yeah, I thought it was very reminiscent actually. I was like, oh, it's linear regression 2.0.
Yeah, and I think that often happens, like, because it does say in the book that this came, say, more through computer scientists, and often like different fields discover basically the same things, just in like a completely different language or like form of representing stuff.
Yeah, for sure.
Usually is good for science if that happens, or it's powerful when that happens, like it's an indicator that both fields are onto something.
Yeah, absolutely. The interdisciplinary approach and being able to apply robust theories and mathematical formula or concepts to a research question is really powerful. It's actually something like I know we discussed it a couple of weeks ago with that neuroscientist who uses physics. I think it's really cool when science does that, when they're not afraid to borrow when obviously it's applicable and when it's robust and valid, when they're not afraid to borrow from other fields. I think it makes science better. Sorry, that was a slight tangent, but it was very talk. So that was just a little discussion point, which actually is what it was for. So no, nothing bad there. We're going to go a little bit into some of the practical visualizations of nonlinear kernels in practice. I've only performed, I think, like one sample from the lab. So we're happy to talk more about the stuff I've done or the stuff I haven't done as well. And hopefully this one renders. It did when I checked last, and I don't have to follow up with a visualization, but we'll see. So just for the interest of transparency, this is the code where I generated a data set. Now this data set follows a nonlinear decision class boundary. So we can't set our kernel argument to linear, unlike last time. So instead, if we look at this first, I think it's very useful to look at your data before you do anything. So this is not separable by a line, right? I can't cut down the middle. I can't find a linear relationship where I say, yeah, that's blue, that's red. There's something much more donutty going on. I will die on the hill that the data is looking donutty here. So again, this is the code I used to generate this visualization. So we're all on the same page. So as a note, the estimator doesn't change, so the SVC doesn't change. We can still use that in nonlinear decision boundaries. But in this case, obviously, we can't use a linear argument for our kernel parameter. In this case, as we've looked at some of the options before, it's probably going to be, well, actually, I know I say polynomial kernels are here before, but do you guys think, do you guys know why we might use polynomial kernel for this type of data? Because obviously we have the other option. So why could we use the RBF kernel as well? What are your thoughts when you look at this nonlinear data, or in this use case of nonlinear decisions?
Yeah, I would think you can basically achieve the same with the radial
Yeah,
kernel.
yeah.
Because all you're really sort of you can just imagine like drawing two lines,
Yeah,
right? Like as in like basically getting the same visualization as when you like, or the book visualizes the support vectors. And you can imagine just almost a rule that says like if the distance from those lines, is greater than just say they're all blue. And if
Sure.
they're like within, okay, just say they're red. So you can, maybe it's not right to say like you can imagine, but when you've seen enough data that has this type of, like these type of relationships, you can imagine that if you reflected at the right point the data, you'd be able to get like essentially a linear separation.
For sure.
Like if you drew a mirror image at the right point, you should be able to.
Yeah, exactly. I think, I don't know if I've actually put it in my quarto, but I did experiment with both the RBF and the polynomial, and it was interesting actually. They both managed to do a pretty decent job of classifying, so 100%. And as an aside, this is just for use of Python, when we are working with polynomial kernels, we can also use the degree argument to specify the degree for the poly parameter. So kernel quad poly. So whilst when we fit with a radial kernel, we specify a value of gamma here. So I think I actually used a radial in this use case. Been like a week since I've been here. So yes, I specified gamma as 1, and I actually assigned 1 to the C parameter as well. So looking at this, how do we think the RBF has done in terms of classification? I think like it's pretty much done like what Jack's described in terms of drawing around it actually.
Yeah, it's done pretty well. You think it's quite close to, when they call it like the Bayes classifier, as in there are points in the original feature space that you're not going to be able to separate, as in like the information just isn't there.
Yeah.
But because some of the red is directly in like was it? I can't remember which one was red or blue now. I feel like it's sort of been switched.
Yeah.
But yeah. Yeah, it seems to have done, I mean, it's done quite well. And you would probably like, this does actually go back to kind of that main intuition about why do you want to be okay with misclassifying some data?
Yes.
Like that was the idea where you could have points, like the support vector machine came in because you could have points that you like intentionally were fine with misclassifying to do better on the others. And those ones that it's misclassifying that are actually in with the other label, like as in with the other classification, that I think that's a good example of a situation where you would actually want to misclassify those data points. You wouldn't want to draw a super squiggly line around them.
Exactly. Yeah. I think it's a very good point.
Question.
Yes.
Because we looked at like tuning parameters C and gamma, and it just appears they're on similar log grid. Do they tend to be sort of similar values in different use cases?
Sorry, Sharon, could you repeat the question?
Oh yeah. So in terms of tuning parameter C and gamma,
Yeah.
they're measured on similar log grids. Do they tend to adapt like similar values? This is just a like out of the box like question.
No, that's a really good question. I will be completely honest, I don't know. I will probably need to experiment with like tuning the parameters, seeing what it looks like when I tune them and I make C smaller, and vice versa. But I don't know.
Shouldn't they be inversely proportional? As in, when C is high, you're saying I've got a high budget for errors, so I'm going to let a lot of data into this margin and I'm going to reduce the amount that I draw around. I'm going to reduce the flexibility.
Right. Yeah.
Whereas with the gamma parameter, when C is high, so let's say it's like 0.1 instead of 0.01, I'm at that point, I'm reducing flexibility. So like a high C is kind of proportionate to a low gamma.
Right.
At least if I haven't done the gymnastics
Yeah. Okay.
kind of wrong.
That's interesting.
So it's like an inverse relationship, essentially, roughly.
Yeah, you'd want to achieve. I need to definitely double check this, but I think you would want to achieve the same thing. Say if you are using like the RBF, like with the gamma parameter, you're gonna, let me just make sure I got this. You're gonna lower that. So you're gonna like increase the negative exponent, as in go 10 to the 3, 10 to the 4, make that value smaller. And that's going to give you a more flexible classifier, which is going to do better on training, but probably at the expense of testing. Whereas with the with C, if you have C as effectively 0, like you're not allowing any like space in that margin, you're like not, is this right? That you're not going to fit the training data at all. Yeah, so when C is small, yeah. Oh no, maybe it is the same way. Because when C is 0, that's when it's highly fit, right?
Yes. Yes. Yeah.
Yeah, sorry, no, they should be proportional then.
Okay. Okay.
Right, cool.
Okay.
Sorry, I did the thing where it feels like C should be the other way around.
It's confusing. I honestly I have to force my brain to not think that way. I think when I was writing this, I had to change the sectional tuning parameters like twice because my brain really wanted it to go intuitively. And I was like, no, that's not what the book says. You're making things up. Don't do that. I had to reverse it. So yeah, that seems logical that they're proportionate. Given that I've set them at 1 as well, and this is the outcome visually. So sorry, Sharon, Jack answered that question. I generally didn't. Thank you,
No,
Jack.
I'm not sure. I might have completely misanswered that question.
No, I definitely think you answered it, and I think yes, I think it was a revelation into the wonders of parameter counterintuition. So just a little quick kernel comparison I just did, just to, again, we know this is purely for a use case or very self-evident, ta-da, this is why you don't use linear. We know visually you wouldn't use linear for this, but if we look at a very brief model performance, we can obviously see that the radial approach is a lot better at classifying than linear. I know the sky is blue, but it would be interesting next time when I do include the polynomial to see how they compare. I can add in the model performance here. And I did add in a little bit of a discussion point as well. Jack really astutely noted how you kind of draw around the data points for the classification. What kinds of data? I mean, we're never going to get the ideal real world data, rarely. We can dream, but in which kind of use cases or data types do you think might be best, or say best, might be appropriate for this type of radial approach?
I would think, to give it like maybe like if you use like a concrete example, say if like 3 p.m. is the peak of number of people walking down a street, right? As you get further away from 3 p.m. either side, like whether you're too early or you're too late, the traffic's going to drop right off. So you could kind of imagine that if you that's like something that's going to have like a real U shape in the frequencies, as in like at 6 a.m. there's going to be very few people walking.
Sure.
Then as time goes by, so if time is the x-axis, at 12, 1, 2, it's going to be picking up, and then 3, it's going to peak. And then 4, 5, 6 might be quite similar to 2, 1, 12. And then like 8, 9, 10, 11 o'clock at night, it's going to be a bit more like 3 a.m. or like, yeah. And if you just rearrange your data so that it's not the absolute value, but it's like the distance in time from the peak, you can, that line, if you wanted to, you could turn it into polar coordinates, and you would see like, you'd be able to basically guess what time it was based on the number of people walking down the street. You'd be able to apply this transformation and separate that data kind of easy. And it's always, or not always, but it's usually going to be the case that you want some kind of process that has like kind of just symmetry, like not so much of something, a lot of something, and then not so much. That's when you're going to be able to like nice and easily separate it using something like a radial transformation.
That's really cool. That's a really interesting use case. I'm wondering if you can compare it culturally as well, because Spain at 10 p.m. is like dinner. So it would be interesting to see footfall in different countries.
Yeah. Imagine if you were like counting how many people are eating dinner in a country.
Yes, yeah, exactly.
Like, basically, no one's going to be eating dinner like very early in the morning.
Yeah.
And in the UK, no one's going to be eating it very, very late at night. But in Spain, a lot of people are going to be eating it very late at night.
Exactly. Funny.
So yeah, you would have to change if you had the variable like this country is Spain, country is UK. That would help you classify. Should help you, and you would apply a transformation, or you could apply a transformation to the data like this that should help you.
It's very interesting. Oh, that's a cool use case. Just one final section for today. I made it very brief, unfortunately, but hopefully gives us a bit of an idea for evaluating our support vector machine performance. And I know Jack mentioned it briefly earlier on, the ROC curves. So again, I've done something really generic. This is, I feel like I'm kind of swindling people by putting such stark contrasts in. But I've just included the comparison between obviously the RBF and the random classifier. And I've put a very generic kind of watch out for this if you're kind of understanding how to interpret the ROC curve. I've kind of seen it as the more the curve kind of bows towards the left corner, the better your model distinguishes between classes, in a very general, quite crude way of putting it, but just to give you a sense of, okay, like how is my model performing? And I didn't read so much into this section. I've just included it here in terms of like the mathematical notations, and also a little bit of explaining like the output decision scores. And that by varying our threshold for classification, we can, as we mentioned before, trade off between sensitivity and specificity. But if anyone wanted to talk a bit more about ROC curves in general, feel free to throw your name in the hat, because this is something I didn't really have much time to read up on, but I included it for completeness.
Well, one thing so on this is like if you look at the x-axis and y-axis labels, like true positives are good, right? So like higher values of that are going to be better. To the top of that is better than at the bottom. And like conversely on the x-axis, false positives are bad. So a lower value of false positives, i.e. 0, like going to the left, that is better than a higher value of false positives. So your like absolutely optimal classifier gets like 0 false positives and 100% true positives. So you get like 1.0 and 0.0, right? And that would be just like let's say a point in the absolute top left.
Yeah, exactly.
Yeah. So yeah, it kind of the curves can be quite weird, and it maybe takes seeing them a bunch of times to kind of get a feel for them, especially like when they're not so obvious as this one, where this is just like obviously a very good classifier. Yeah, it kind of follows from just sitting and inspecting the x-axis or the axes, like where the optimal case is, and that's high and left. And so like as you drift lower and right, it's like you're doing slightly worse.
Yeah, I think I didn't have time to include the lab stuff from the book, but the book lab stuff has some good ROC examples, like of that what you described, different instances where there is a strange looking curve or the lines seem very close together, and it's useful just to sit with your eyes and look at it and look at that, the X and Y. But this was very much like, here is the perfect ROC curve, which you'll probably never see in the wild, but enjoy, get used to what the curve looks like from the top left. But yes, so that is so that's been the chapter on support vector machines. And I thought it was very enjoyable. I thought it was very interesting. Brought me back to a lot of the logistic regression stuff. And I hope you guys found the chapter as fruitful as I did. I thought it was really useful.
There was, sorry, you might remember, Sophie, like just off the top of your head, but there was one point, I don't remember if it was in the labs or at the end of the chapter, but it was, I think it was comparing or showing the difference with the LDA classifier and showing the ROC-AUC curves. And it was saying like, okay, it looks like SVM is maybe like slightly better here, but, and it looks better slightly better on the curves and stuff, but they were saying like the difference isn't statistically significant. That's quite a, I don't know, maybe just something to watch out for always going forward, is that, especially when you have quite a low sample size, is like differences in performance that are, you're talking like a few percent, they're not going to be so robust necessarily. So you might look at the ROC-AUC curve and be like, yeah, I'll take that one. That's got to be the best model. But if that model is quite a lot more like, say, complex or flexible, and is only doing slightly better, and your sample size is not so high, then actually maybe the simpler model that's doing slightly worse on the ROC-AUC curve is the one you're going to want, which I thought was quite like an interesting point that they were making.
Yeah, definitely. Like the idea that, okay, just because this flexible method is producing fewer training error rates, that doesn't always mean you're going to have like really improved performance on your test data. That was a really nice little use case that I forgot to include, but please look at it, guys, listening to the video. It's a very nice little section. But yes, thank you guys. I'm going to stop sharing now.
Okay, let me